Right now, a radio signal generated by 23 watts of electrical energy is cutting through 13 billion miles of frigid vacuum, carrying scientific measurements from a realm where the sun is little more than an intensely bright star. On August 4, 2026, flight operations controllers at NASA's Jet Propulsion Laboratory received confirmation that a daring, months-in-the-making engineering maneuver executed across the vastness of space had succeeded without a single glitch. By remotely reconfiguring the thermal architecture of Voyager 2, engineers managed to recover a minuscule 10 watts of electrical margin, an amount of power so tiny it wouldn't illuminate a nightlight, yet significant enough to keep 3 vital cosmic sensors operating for an additional 12 months in interstellar space. But as these ancient instruments continue to sample the unshielded environment beyond our solar system, they are returning data that defies standard astrophysical predictions about the boundary where our sun's domain ends. In fact, there is one specific thermal reading recorded by this 49-year-old probe that fundamentally challenges our baseline understanding of interstellar physics, a figure so astonishingly high that researchers spent months double-checking calibration curves before accepting what the probe was actually registering. How could a region of deep space long assumed to be a freezing void exhibit temperatures hotter than the surface of many stars? We will uncover that exact mystery in just a moment. But to understand why this recent power rescue was such an incredible gamble, you first have to realize where Voyager 2 actually is and what it took to get there across half a century of deep space flight. Every second this probe survives, it pushes human knowledge deeper into uncharted territory, opening new questions about the true nature of the cosmos that will keep scientists analyzing data for decades to come, proving that even a tiny spark of electrical energy can illuminate the dark reaches of our galaxy. To grasp why a 10-watt power savings in deep space has captivated planetary scientists across the globe, it helps to look back at how this iconic robot reached the edge of the galaxy in the first place. Voyager 2 commenced its historic journey on August 20th, 1977, lifting off 17 days prior to its identical twin, Voyager 1. While that numerical ordering might sound counterintuitive given their official names, mission planners deliberately dispatched Voyager 2 along a broader, more leisurely flight arc. This specialized trajectory took advantage of a rare celestial alignment that occurs only once every 176 years, granting the probe gravity assist maneuvers from planet to planet along a path famously known as the Grand Tour. By slingshotting through the gravitational wells of giant planets, the spacecraft gained immense speed without burning precious onboard propellant. Voyager 1 was assigned a much faster flight path targeting Jupiter and Saturn exclusively, allowing it to reach interstellar space decades ahead of its sister craft. Meanwhile, Voyager 2 pulled off a grand slam of outer solar system exploration, conducting historic, unprecedented close encounters with Jupiter during 1979, Saturn back in 1981, Uranus during 1986, and Neptune by 1989. To this day, Voyager 2 stands as the only spacecraft created by human hands to ever visit the icy realms of Uranus and Neptune, meaning practically every close-up image, magnetospheric map, and direct atmospheric measurement we possess of those distant ice giants originated from hardware assembled during the Nixon administration and launched during the Carter presidency. Consider the technology of that era. Voyager 2's flight computer relies on magnetic tape recorders and 8-track era memory systems with less computing capacity than a modern digital car key or pocket calculator. Yet both spacecraft were initially built to operate for a primary mission duration of just 5 years. Neither spacecraft has stopped working. Today, Voyager 2 is approaching its 49th year of continuous operational service, nearly 10 times its original design lifespan, and it is doing so while traversing a regime of space where no human hardware had ever ventured prior to the current decade. Power, however, has become the ultimate limiting factor governing the mission's remaining longevity. Both Voyager probes rely on radioisotope thermoelectric generators, which convert heat emitted by the natural radioactive decay of plutonium-238 isotopes into usable electrical current. When Voyager 2 departed Earth in 1977, its power system generated roughly 470 watts of electricity. But radioactive decay is inexorable. Every passing year reduces the plutonium's thermal output, causing electrical production to drop by approximately 4 watts annually. As the decades accumulated and available wattage plummeted, flight controllers at NASA were forced to initiate a carefully prioritized deactivation sequence. First went the non-essential chassis heaters, followed by redundant engineering subsystems, and eventually individual scientific sensors whose planetary objectives had concluded decades ago following the Neptune encounter. Out of the 10 original scientific instruments carried aboard Voyager 2, systematic shutdowns had trimmed the active payload down to just 3 operational units by early 2026: the magnetic field detector, plasma wave monitoring package, and galactic cosmic particle analyzer. Think about that for a moment. A machine traveling thousands of miles per hour, through the dark, stripped down to its absolute bare essentials, yet still sending back world-changing data from the dark. Each of those 3 surviving sensors represents a priceless window into the unknown, which made the impending loss of even one instrument completely unthinkable to the engineering team. Without drastic intervention, the cosmic ray sensor was scheduled to be powered down forever prior to 2026 drawing to a close, leaving the probe severely handicapped and shutting down a decades-long record of interstellar data collection that cannot be replicated by any ground-based observatory or space telescope anywhere on Earth. This dire scenario set the stage for one of the most audacious engineering maneuvers in NASA's long history, requiring unprecedented ingenuity to pull off safely. Without the radical intervention recently confirmed by NASA engineers, that 3-instrument science payload was on the verge of shrinking even further. Mission schedules had dictated that the Cosmic Ray Subsystem, an essential instrument responsible for counting high-energy atomic nuclei originating from violent galactic events, would have to be permanently powered down before the conclusion of 2026. Such a loss would have reduced Voyager 2 to just 2 functioning science sensors, severely hampering its ability to conduct comprehensive multivariable research outside our solar system's protective envelope. That is precisely why the success of the August 2026 power reconfiguration represents such a monumental triumph for space exploration. The procedure, nicknamed the Big Bang by mission controllers at the Jet Propulsion Laboratory, managed to reclaim approximately 10 watts of electrical capacity. In everyday terms on Earth, 10 watts seems completely insignificant. It is less energy than a standard smartphone fast charger draws from a bedroom wall socket. But out at the lonely frontier of interstellar space, where a probe loses 4 watts of electrical production every 12 months due to natural nuclear decay, 10 watts acts as an absolute lifeline. It effectively buys 2.5 full years' worth of power decay offset, ensuring that all 3 remaining science instruments can continue collecting priceless data straight through 2027 and potentially well into the future. Now here's where it gets strange. How do you pull off a high-stakes electrical overhaul on an irreplaceable robot operating billions of miles away without accidentally killing it permanently? The core of the maneuver involved fundamentally altering how Voyager 2 maintains the temperature of its critical thruster fuel lines. To keep hydrazine liquid fuel from freezing solid in the near absolute zero cold of deep space, the probe had historically relied on 3 dedicated electrical resistance heaters. The engineering team realized through months of rigorous computer modeling that they could safely shut down those 3 dedicated line heaters if they simultaneously enabled 3 alternate onboard electrical devices. These alternate devices generate adequate waste heat as a byproduct of their regular operations to keep the thruster lines warm, while drawing 10 fewer watts of total system power overall. Grounding this achievement in concrete numbers highlights just how razor-thin the probe's operating margins really are. Voyager 2 currently operates on less than 200 total watts of electrical power, roughly 1/3 of the electricity consumed by a standard home desktop computer. Freeing up 10 watts within such a tightly constrained energy envelope is the operational equivalent of finding an extra hour of battery life on a smartphone that is already sitting at 2% power, while knowing that if you mess up the settings for even a second, the phone turns into a permanent brick. Planetary scientists knew that losing even one of the remaining 3 instruments would blind us to crucial cosmic interactions that cannot be measured from Earth or anywhere else inside the solar system, making this daring maneuver an absolute necessity for the future of interstellar science. The sheer audacity of executing a high-stakes remote hardware switch on a 50-year-old computer system left the engineering team holding their breath for nearly 2 days while waiting for the telemetry to return. When the signal finally arrived, confirming full system stability, the relief across JPL was palpable, marking one of the greatest engineering saves in spaceflight history and guaranteeing another year of breakthrough scientific discoveries that will continue to reshape our understanding of the outer universe and inspire future generations of space scientists across the globe. Understanding the sheer difficulty of this feat requires contemplating the immense distances and lag times involved in communicating with the outer edge of our solar system. Voyager 2 is currently situated over 13 billion miles from Earth, a distance corresponding to roughly 119 times the gap between the Earth and the Sun. At that staggering scale, physical intuition breaks down completely. Consider the velocity of light itself, which travels at an incredible 186,000 miles per second. When engineers at the Deep Space Network send a radio command to Voyager 2, that signal takes over 19 hours just to reach the spacecraft. Once the onboard computer executes the command, the probe's reply must travel another 19 hours back across the cosmic void before reaching receivers on Earth. In total, controllers must wait nearly 39 hours, almost 2 full days, between pressing the send button and learning whether their instruction worked or catastrophically failed. Imagine trying to play a high-stakes game of chess where you make a move on Monday morning, but you cannot see whether your piece landed on the correct square until Tuesday night, and if you made a single miscalculation, your entire board instantly vaporizes into thin air. That is the daily reality faced by the flight team at Jet Propulsion Laboratory. To make matters even more incredible, the radio signal returning from Voyager 2 leaves the probe's transmitter at a modest 23 watts, which is about the same wattage as a bulb inside a kitchen refrigerator. By the time that signal completes its 19-hour journey across 13 billion miles, the electromagnetic wave has spread out over millions of miles of empty space. When it finally strikes the massive parabolic dishes of NASA's global deep space tracking infrastructure located in Goldstone, California, Madrid, Spain, and Canberra, Australia, the signal strength is measured in attawatts, a billionth of a watt. Extracting coherent data from such a faint whisper requires combining the collecting power of multiple 70-meter radio dishes and filtering out background noise using ultra-sensitive cryogenic receivers cooled near absolute zero. Furthermore, that stream of interstellar data arrives at a rate of just 160 bits per second. To put that in perspective, a standard dial-up internet connection from the 1990s was nearly 300 times faster than Voyager 2's deep space link. At 160 bits per second, downloading a single modern high-resolution smartphone photograph would take days of uninterrupted transmission. Yet through this microscopic trickle of digital information, humanity is receiving its only direct, on-the-spot reports from interstellar space, proving that human engineering can bridge even light hours of separation. Every single byte received is a triumph of mathematical signal processing and deep space tracking, representing a victory over distance that defies imagination. It is a technological miracle operating on the absolute bleeding edge of physical measurement, linking a team of engineers on Earth to a lonely robotic ambassador cruising through the galactic dark at over 34,000 miles per hour, refusing to go quiet without a fight, pushing the boundaries of human achievement further than ever before into the uncharted infinite. The technical execution of the Big Bang procedure reveals just how meticulously NASA engineers must plan every single command string sent into deep space. The central challenge of the maneuver was that it could not be performed sequentially. It had to occur as a synchronized, simultaneous swap. The spacecraft's attitude control thrusters rely on liquid hydrazine fuel to make tiny rotational adjustments that keep its high-gain dish antenna pointed directly toward Earth. Hydrazine freezes at approximately 2 degrees Celsius, roughly 35 degrees Fahrenheit. If the hydrazine fuel lines were allowed to cool down below that threshold even briefly, the liquid fuel would crystallize into solid ice, expanding and permanently bursting the fuel pipes. Without active thrusters, Voyager 2 would lose its orientation, its dish antenna would drift away from Earth, and contact with humanity would be lost forever within hours. Therefore, cutting power to the primary line heaters required the alternate heat-generating equipment to come online at the exact same instant. If there had been a delay of even a few minutes in the thermal transition, the fuel lines could have begun dropping toward critical freezing thresholds before the replacement heating mechanism took effect. To minimize mission risk, flight engineers decided to test the thermal swap procedure on Voyager 2 prior to attempting it on Voyager 1. This decision was based on two practical factors. First, Voyager 2 is positioned somewhat nearer to home than its twin, which reduces the communication delay cycle by several hours. Second, Voyager 2 possessed a slightly larger power margin than its twin, making it a safer candidate for experimental testing. During May and June of 2026, controllers sent preliminary test commands to verify how the alternative heating circuits responded under real space conditions. Once telemetry confirmed that the alternative equipment could maintain proper thermal equilibrium, the engineering team authorized the full operational transition. Commands were uplinked across the 13 billion mile gap, and on August 4th, 2026, confirmation data beamed back to Earth showing the swap had succeeded flawlessly. The line heaters were safely powered down, the alternative systems were operating as expected, and 10 watts of power had been successfully liberated. With the procedure validated on Voyager 2, NASA plans to execute a similar Big Bang power reconfiguration on Voyager 1 in the coming months, extending the operational life of humanity's most distant space probe as well. But why go through all this incredible stress for a probe launched half a century ago? Why risk everything to keep 3 aging instruments powered on? The answer lies in what Voyager 2 found immediately after crossing the boundary of our solar system, where conditions proved far wilder and far more turbulent than anyone had predicted in computer simulations. The raw data coming back from the probe was revealing a cosmic structure that reshaped astrophysics overnight, forcing scientists to rethink how our solar system interacts with the Milky Way galaxy and demonstrating why keeping these instruments online is worth every single watt of recovered power, regardless of the immense technical difficulties involved in managing hardware operating on the dark edge of interstellar vacuum, far beyond the reach of human hands. While recovering 10 watts of power is an engineering masterpiece, the true significance of this accomplishment lies in what those three remaining science instruments are actually measuring. Voyager 2 is not merely coasting through an empty cosmic desert, it is actively sampling the local interstellar medium, representing the celestial domain situated completely beyond the protective bubble generated by our Sun. This solar bubble, known to astrophysicists as the Heliosphere, is one of the grandest yet least visible structures in the solar system. It is created by the solar wind, a continuous torrent of charged plasma flowing outward from the Sun at speeds of up to 2 million miles per hour. This supersonic wind pushes against the surrounding galactic environment, inflating a giant magnetic envelope that encompasses all 8 planets, the main asteroid belt, and the distant Kuiper belt. The outer boundary, where pressure exerted by solar outflow matches the pressure of the surrounding galactic environment, is designated as the Heliopause. On the solar side of this threshold sits solar territory, while outside lies true interstellar space. The heliosphere acts as a vital shield for our planet, deflecting the vast majority of high-energy galactic cosmic rays generated by supernova explosions and neutron star collisions throughout the Milky Way. Without this magnetic umbrella, ambient radiation levels across interplanetary orbits would be dramatically higher, posing serious challenges for planetary habitability over geological timescales. Voyager 1 became the first human craft to cross the Heliopause on August 25, 2012, at a distance of 121 astronomical units. Voyager 2 followed on November 5, 2018, crossing at 119 astronomical units along a different trajectory. But when Voyager 2 made its historical crossing, it possessed something Voyager 1 lacked, a fully operational plasma science instrument. When Voyager 1 crossed 6 years earlier, its plasma detector had been dead for over 3 decades due to a hardware failure in 1980. Voyager 2, however, carried a working plasma sensor across the boundary, giving scientists their first direct measurements of interstellar plasma density and temperature. And what that sensor recorded astonished the scientific community. According to data returned by Voyager 2, the plasma immediately outside the Heliopause registered temperatures between 30,000 and 50,000 Kelvin, or roughly 50,000 to 90,000 degrees Fahrenheit. That is hotter than the surface of most stars, existing right on the doorstep of our solar system. Scientists had anticipated a cold, tranquil void, but instead found a raging thermal barrier wrapping around our cosmic home, creating a profound scientific paradox that researchers are still struggling to fully explain using existing theoretical frameworks and traditional astrophysics models, proving that interstellar space is far more complex than previously assumed by ground-based observations. To anyone unfamiliar with astrophysics, hearing that interstellar space reaches temperatures of 50,000 degrees sounds like a contradiction in terms. We are taught from childhood that deep space is a freezing void near absolute zero. So how could the medium outside our solar system be scorching hot? This is where rigorous scientific nuance becomes essential and where popular headlines often oversimplify the reality. Scientists emphasize that there is a fundamental distinction between kinetic temperature and thermal energy density. Temperature in astrophysics is a measurement of how fast individual atoms and ions are moving. In the interstellar medium, particles are traveling at extremely high speeds, which translates mathematically to a kinetic temperature of tens of thousands of degrees. However, the density of those particles is unimaginably low. There are only a few individual ions scattered per cubic inch of space. Because the particle density is so sparse, there are virtually no atoms available to transfer heat to a physical object. If an astronaut were to step outside a spacecraft in this region, they would not feel heat at all. In fact, their body would rapidly lose heat through thermal radiation because there are simply not enough energetic particles colliding with their skin to transfer heat into their body. Furthermore, astrophysicists continue to debate what actually causes these elevated temperatures near the heliopause. Some researchers argue that the extreme temperatures recorded by Voyager 2 do not reflect the ambient, undisturbed state of the Milky Way galaxy. Instead, they suggest that what Voyager 2 measured is a localized compression zone, a thermal boundary layer where the expanding solar bubble collides with and compresses the incoming interstellar material, creating a localized shock zone that heats up the plasma. Another layer of complexity comes from the striking differences observed between the two Voyager crossings. When Voyager 1 crossed the Heliopause in 2012, it detected intense magnetic field turbulence and dramatic directional shifts. But when Voyager 2 crossed in 2018 at a different location, its magnetometer observed almost no turbulence, recording a smooth transition in the magnetic field lines. This discrepancy proves that the boundary of our solar system is not a uniform, smooth sphere like a billiard ball, but rather a dynamic, turbulent, and asymmetric structure that changes depending on where and when you measure it. With only 2 spacecraft having ever traversed this boundary, scientists candidly admit that our empirical dataset is extraordinarily sparse, making every new data point priceless for refining our cosmic models and preventing premature conclusions about the galaxy at large, ensuring that debate remains open and active among leading astrophysicists who continue to analyze the incoming telemetry. Despite these ongoing scientific debates, what is indisputable is the unprecedented value of the empirical data being gathered by Voyager 2 right now. Thanks to the success of the Big Bang maneuver, all 3 of the probe's remaining instruments are actively measuring different facets of the local interstellar medium, returning concrete facts that no computer simulation could ever replicate. The magnetometer is directly recording the strength and orientation of the interstellar magnetic field, a force field shaped by ancient stellar explosions that took place millions of years ago across galactic history. Simultaneously, the Plasma Wave Subsystem is measuring subtle oscillations in the surrounding electron plasma, allowing scientists to map out how the electron density fluctuates as the spacecraft moves deeper into space. This is the exact same instrument that previously detected a persistent, low-frequency plasma hum on Voyager 1, providing a continuous acoustic-like signature of interstellar density. Meanwhile, the cosmic ray subsystem, the very sensor saved by the 10-watt power recovery, is measuring the raw, unfiltered stream of galactic cosmic rays arriving from deep space. By comparing these interstellar radiation readings with data collected by satellites inside the solar system, researchers can calculate precisely how effective the sun's magnetic shield is at blocking cosmic radiation. The data has already shown that the heliosphere's protective efficiency varies in tandem with the sun's 11-year solar cycle. During solar maximum, when solar activity peaks and solar wind pressure increases, the heliosphere inflates slightly, offering enhanced radiation protection. During solar minimum, the bubble contracts, allowing a higher flux of cosmic rays to penetrate the inner solar system. Additionally, the fact that both Voyager probes crossed the Heliopause at nearly identical distances, roughly 119 to 121 astronomical units, despite traveling in vastly different directions, has forced scientists to revise older models of the solar system's overall shape. For decades, textbooks depicted the heliosphere as having a long, comet-like tail streaming behind it as the sun orbits the center of the galaxy. The Voyager data suggests instead that our solar system's protective bubble may be much more spherical, closer in shape to a giant cosmic beach ball. Though with significant localized ripples, magnetic irregularities, and structural distortions that vary across space and time, giving us an entirely new perspective on our celestial environment and changing how we view our place in the galaxy for generations to come, providing solid ground amid galactic mysteries, and replacing speculation with empirical truth that grounds our cosmic models. Looking toward the immediate future, the successful power reconfiguration on Voyager 2 has set the stage for the next major milestone in deep space operations. In the coming months, flight engineers at Jet Propulsion Laboratory plan to apply the same Big Bang procedure to Voyager 1, which is currently cruising through interstellar space at a distance of over 15 billion miles from Earth. Voyager 1 is traveling on a steeper trajectory out of the ecliptic plane, and its signal currently takes more than 23 hours to reach Earth. On November 18, 2026, the older Voyager 1 probe is slated to cross a monumental symbolic threshold. It will become the first human-made object in history to reach a distance of precisely 24 light hours away from our planet. At that moment, a radio signal sent by NASA's deep space communication antennas will take a full 24 hours traveling at the speed of light just to reach the probe, and another 24 hours for a response to return, requiring a 2-day round trip for a single back-and-forth communication. Voyager 2, traveling along a slower trajectory, is not expected to reach the 1 light day mark until November 2035. Whether Voyager 2 will still be operational by that date remains uncertain, but the 10-watt power buffer recovered in August 2026 has dramatically improved the odds of continued scientific output during 2027 and potentially into the early 2030s. If the hardware holds up, engineers hope to keep at least one scientific instrument running on both spacecraft until plutonium decay finally drops power levels below the threshold required to run the main transmitter. What makes the ongoing operation of these spacecraft so vital is that there is no replacement waiting in the wings. Every other space probe launched by humanity, including New Horizons, which famously visited Pluto in 2015, is either traveling too slowly or lacks the nuclear power margin required to operate science instruments at such extreme distances. Even if space agencies were to fund and launch a dedicated high-speed interstellar probe today, it would take at least 2 to 3 decades of continuous travel just to reach the Heliopause boundary, where Voyager 2 is currently operating. The measurements being beamed back right now through Voyager 2's refrigerator bulb transmitter are genuinely irreplaceable. Every single watt saved by the engineering team represents months of unique data that cannot be collected by any other instrument in existence for at least a generation, ensuring that Voyager 2 remains the premier laboratory at the edge of the galaxy, carrying our scientific ambitions into the dark and inspiring future generations of interstellar explorers who dream of venturing beyond our solar shores into the grand cosmic unknown. This brings us back to the central mystery we introduced at the very beginning of our story, the astonishing discovery that interstellar space outside our solar system is filled with plasma registering kinetic temperatures between 30,000 and 50,000 Kelvin. Without the daring 10-watt power reconfiguration confirmed on August 4, 2026, humanity would have lost one of its primary eyes watching this scorching cosmic frontier prior to the conclusion of 2026. Instead, a 49-year-old robotic explorer, operating on technology designed before the invention of the personal computer, continues to rewrite astrophysical textbooks from 13 billion miles away. It serves as a profound testament to human ingenuity that a tiny probe powered by decaying nuclear heat, transmitting signals no stronger than a nightlight across a 2-day communication delay, can still expand the horizons of human knowledge. As Voyager 2 presses deeper into the uncharted void between the stars, it continues to remind us that the universe beyond our solar bubble is far stranger, far hotter, and far more dynamic than we ever imagined. The open loop of interstellar exploration remains active. And as long as Voyager 2 continues transmitting, humanity will keep listening attentively to every faint whisper sent back by our species' most distant robotic scout. Where will Voyager 2 lead us next? Only time and 10 precious watts of power will tell. Every transmission is a gift from the deep, carrying the story of humanity's unending quest to comprehend the universe.